Almost everything you were taught about the moon is either incomplete or wrong, and a single photograph taken from the window of a spacecraft called Integrity has just made that impossible to ignore. For 53 years, we thought we understood our closest neighbor. We had the Apollo samples, rock fragments sealed in nitrogen since the Nixon administration. We had the maps, the laser altimetry, the gravity surveys, the cratered face we've all stared at since childhood. The consensus was clean. The moon is a dead rock, a finished story, a museum piece in the sky. That consensus is breaking, and the photographs that came back from Artemis 2, the first crewed mission around the moon since Apollo 17, have pushed the crack wide open. This is the story of what those 4 astronauts actually saw, why it matters far more than the press coverage suggested, and why almost everything you thought you knew about the moon may need to be rewritten. Start with what Artemis 2 was supposed to be on paper, a shakedown flight. 4 astronauts, Reed Wiseman as commander, Victor Glover as pilot, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen as mission specialists strapped into the Orion capsule they had nicknamed Integrity. Their assignment was simple: launch on the Space Launch System rocket from Kennedy Space Center on April 1st. Fly a free return trajectory around the far side of the moon. Don't orbit, don't land, test the life support, the heat shield, the communications, the re-entry profile, come home 10 days later. But the crew carried something Apollo never did. Modern cameras, high dynamic range sensors capable of capturing detail in deep shadow that film in 1972 simply could not resolve. Handheld bodies with 400mm lenses. And when Integrity swung behind the moon on April 6th, the crew did what any human would do with that view outside their window. They pointed the cameras and they kept shooting for 7 hours, working in shifts. They took roughly 10,000 photographs. The closest approach came within 4,067 mi of the lunar surface. And at peak distance, they reached 252,156 mi from Earth, breaking the Apollo 13 record for the farthest humans have ever traveled from home. During the flyby, Integrity passed through Earth's shadow, and the crew witnessed a total solar eclipse from deep space lasting nearly 54 minutes of totality, something no human being has ever seen before. They also caught the faint flashes of 6 meteoroid impacts striking the lunar surface, visible only because they were looking at the dark side with no glare from the sun. All of that would have been historic on its own. None of it is the reason this mission matters scientifically. The reason is the far side. If you were floating alongside Integrity at that moment, looking down as the moon rolled underneath you, you would have seen something almost nobody in human history has ever seen with their own eyes. The entire far side lit by a sun angle no Earth-based telescope can ever capture scrolling past your window. Heavily cratered, rugged, ancient, completely different from the face you grew up looking at. For 40 minutes of the flyby, Integrity was behind the moon with no direct communication to Earth. Radio blackout, the most isolated 4 human beings in history. No one on Earth could hear them, advise them, or help them. During those minutes, Commander Reed Wiseman later described the experience as bending the mind. Not sitting inside a capsule, he said, but transported, completely cut off, looking back at Earth as a small blue crescent dropping behind the lunar horizon. That moment, that specific photograph the crew called Earthset, is already one of the most important images in the history of human spaceflight. Apollo 8 gave us Earthrise in 1968, the iconic blue marble pulling above a gray foreground. Artemis 2 gave us the opposite, home dropping out of view, shrinking into the distance. And when Earth disappeared, what remained was the face of the moon that nobody on our planet can ever see directly. That difference is the real mystery. On the side we can see from Earth, the near side, there are enormous dark plains called Maria. Smooth, flat, relatively young terrain where molten basalt oozed up from below and filled gigantic impact basins billions of years ago, the dark patches that formed the face we've called the man in the moon for centuries. They cover roughly 31% of the near side. On the far side, they cover about 2%, almost nothing. Instead, the far side is a chaotic mess of overlapping craters, older terrain, thicker crust, and basins that never got resurfaced by volcanism the way the near side did. Nobody knows why. This is called the lunar dichotomy, and it is one of the oldest unsolved problems in planetary science. Two hemispheres of the same body formed from the same material at the same time ended up looking like completely different worlds. The crust on the far side is on average about 20 kilometers thicker than on the near side. The chemistry is different, the volcanic history is different, and every theory we have for why this happened is at best incomplete. Scientists have been throwing hypotheses at this problem for 60 years. The first serious idea was simple crust thickness. Thinner crust on the near side meant magma could more easily break through and flood the surface. For a while, that worked. Then the South Pole Aitken Basin on the far side was mapped properly, and it punctured the theory. That basin has the thinnest crust on the entire moon. By the crust theory, it should be drowning in lava. It isn't. Only a few percent of its floor is covered in basalt. The next theory involved a family of elements called creep: potassium, rare earth elements, and phosphorus. On Earth, these elements are spread around. On the Moon, they are heavily concentrated on the near side, particularly in a region called the Procellarum creep terrain. Creep elements are also radioactive. Radioactive elements decay and produce heat, more melting, more volcanism. Geochemical maps from the Lunar Prospector mission confirmed the near-far imbalance, but nobody could explain why creep was there in the first place. Then came the impact hypothesis. Maybe a second smaller moon formed at the same time as ours slammed into the far side and piled up extra crust. Maybe a giant collision on the near side dug out a mega basin and pushed creep material to one side. Computer simulations from Brown University, the University of Münster, and the Macau University of Science and Technology have shown that a low-velocity impact with a roughly 780 kilometers object can reproduce the crustal dichotomy we actually observe. The models work. What we don't have is the smoking gun. And then in 2024 and 2025, China delivered something nobody else had: physical rocks from the far side. Chang'e 6 landed in June 2024 inside the South Pole Aitken Basin, scooped up nearly 2 kilos of lunar material, and brought it back to Earth. It was the first sample return mission from the far side in history. Chinese researchers immediately began running isotopic analysis on those samples, comparing them against Apollo rocks, and the results were genuinely startling. The potassium isotope signatures on the far side were different. The sulfur was different. The iron was different. The numbers suggested that whatever impact created the South Pole Aitken Basin was more energetic than we thought, that it altered the mantle beneath the far side in ways that didn't happen on the near side, and that the lunar dichotomy is likely a direct consequence of that single ancient event. The Artemis II images are now being fed into that analysis. Not because any single photograph solved the problem, but because for the first time in over 5 decades, we have direct human observation of that terrain cross-referenced with modern orbital data from missions like NASA's Lunar Reconnaissance Orbiter, Japan's Selene, India's Chandrayaan probes, and China's Chang'e program. 10,000 frames captured from angles at times and in lighting conditions that no robotic mission has ever produced. One of the first photos released shows Vavilov crater sitting on the rim of the older and larger Hertzsprung basin on the far side. It was taken with a handheld camera at 400 millimeters. The long shadows along the terminator, the boundary where lunar day meets lunar night, accentuate the crater walls and ejecta patterns in a way that orbital images shot from directly overhead cannot. Geologists who have studied this region for decades through orbiter data are now seeing the same terrain at a human eye's dynamic range with shadow geometry that reveals depth, structure, and layering. Here is where the story turns. For the last 15 years, evidence has been accumulating that the moon is wetter, more active, and stranger than anyone thought possible. Chandrayaan-1, India's first lunar mission, detected hydroxyl signatures across the surface in 2009. The L-Cross impactor, NASA's deliberate cratering experiment that same year, confirmed water ice in Cabeus crater near the South Pole. In 2020, the Sophia Observatory found molecular water in sunlit regions, which violated everything we thought we knew about how water survives without shade. Chinese researchers recently identified tiny glass beads scattered across the lunar surface, each one acting like a sponge for hydrogen particles, collectively holding what might amount to hundreds of billions of tons of water across the moon. The picture that has been forming slowly and against decades of orthodoxy is that our moon is not a dead rock. It's a planetary body with a complex, ongoing relationship with water. Ice locked in permanent shadow. Hydrogen raining down from the solar wind. Glass beads trapping molecules like microscopic reservoirs, a system no one predicted in 1972. And yet the body of scientific knowledge that supposedly cemented our understanding was built almost entirely from 6 Apollo landing sites, all of them on the near side, all within a narrow equatorial band. Imagine landing a spaceship in the Sahara Desert and assuming the entire Earth is made of sand. That is functionally what we did with Apollo. The Artemis II images matter because they are the first human-captured visual data of the far side since that era. And the far side is where our model breaks down hardest. Thicker crust, heavy cratering, missing the volcanic flooding that shaped the near side, possibly holding ancient material that was never resurfaced. Scientists are already analyzing the downlinked frames for geological features that orbital data has flagged, but never fully resolved. There's a second layer to this integrity passed over terrain that includes some of the oldest surfaces in the inner solar system. The South Pole Aitken Basin, for example, lies partially on the far side and is the largest confirmed impact structure in the solar system, 2,500 kilometers across 8 kilometers deep. A wound that formed roughly 4 billion years ago when something slammed into the moon and punched almost all the way through the crust. The Artemis II crew did not land there, did not sample it, but they did pass over adjacent terrain and photograph it in conditions that will sharpen our maps of that region, because the next mission that goes there will be human. There's something else worth pausing on because it almost didn't happen. On April 10th, when Integrity slammed back into Earth's atmosphere at nearly 40,000 kmh, the capsule was carrying a heat shield made of a material called Avcoat, same material family used on Apollo. After Artemis I, the uncrewed test flight in 2022, engineers found that Avcoat had behaved unexpectedly. Chunks of it had come loose during re-entry, eroding in a pattern the models didn't predict. NASA spent 2 years investigating, running ArcJet tests, and debating whether to fly Artemis II with the same heat shield or delay for a redesign. They decided to fly it with a modified re-entry profile, steeper and shorter to limit the heating time. The capsule came in hot, plasma building around the hull, the crew pulling nearly 4 Gs of deceleration. For 6 minutes during peak heating, Integrity was in communications blackout. Then the drogue chutes deployed, then the mains, then splashed down in the Pacific off the coast of San Diego at 5:07 p.m. Pacific Time on April 10, 2026. The heat shield did exactly what it was supposed to do, even with its known flaw. That matters because every photograph, every data point, every observation from the flyby only made it home because that heat shield held. Artemis 3 will use a modified AVCOAT formulation. But Integrity's successful return is what cleared the path for the sustained lunar presence that follows. Artemis 3 is scheduled for 2027. It will not touch the lunar surface. It's a test of integrated operations with commercially built landers in low Earth orbit. Demonstrations with SpaceX's Starship and Blue Origin's Blue Moon. Artemis 4, currently targeted for 2028, is the one that's supposed to put boots back on the lunar ground, and where they plan to land is near the South Pole. The South Pole is not an aesthetic choice. It's the region where permanently shadowed craters hold confirmed water ice. It's where the thicker far side crust transitions into the near side. It's where the geology is strangest, the volatiles are densest, and the potential for long-term human presence is highest. Every piece of data Artemis 2 brought back, every photograph of those ridges and terraces and crater rims feeds directly into the mission design for what comes after. And the United States is not the only country with plans there. China's crewed lunar program is targeting 2030 for its first astronaut landing. The Chinese lunar exploration program has already demonstrated capabilities that in some areas exceed what NASA has flown. Chang'e 4 was the first soft landing on the far side in 2019. Chang'e 5 returned samples from the near side in 2020. Chang'e 6 returned the first ever far side samples in 2024. The International Lunar Research Station, a joint China-Russia project, is scheduled to break ground at the lunar South Pole in the early 2030s. In the same general region, NASA is targeting for Artemis 4, which means that the next decade is going to look more like the 1960s than anything since. Two superpowers racing to establish a physical presence on the moon, both targeting the same patch of real estate, both aware that the first country to build infrastructure at the South Pole gets to write the rules for everyone who comes after water. Ice, once it becomes accessible, can be split into hydrogen and oxygen. Hydrogen is rocket fuel. Oxygen is breathable air. Whoever controls lunar water controls the economics of deep space. Artemis 2's photographs are reconnaissance in the most literal sense of the word. Maps of the battlefield before the battle begins. So, what actually changed? Before Artemis 2, our understanding of the far side was built from robotic data alone. Crisp, calibrated, scientifically valuable, but flat. Orbital instruments see from above. They don't see the way a human eye sees with shadow and depth and context. They don't catch meteoroid flashes in real time. They don't photograph a total solar eclipse from the only vantage point in existence, where the moon and sun align perfectly for nearly an hour of totality. After Artemis 2, we have 10,000 frames taken by 4 people in the first human eyes to look at the entire far side since 1972. Those frames, once fully processed, are being compared against every orbital data set we have. Discrepancies are emerging. Features that look one way from above look different when lit from a low sun angle. Shadow patterns reveal terrain slopes and depths that orbital altimetry underestimated. Color variations across ancient lava flows, visible to human perception in a way machines struggle to reproduce, are being cataloged for the first time. 2 small craters near the rim of Oriental Basin were named during the mission. One is now called Integrity after the capsule. The other is called Carol after Commander Reed Wiseman's late wife. Those names will remain on lunar maps for the rest of human history. A small detail, but one that captures something Apollo never had. Continuity. A sense that the return to the moon is personal now, not just political. Wiseman's wife, Carol, passed away in 2020. 5 years later, her husband carried her name to the far side of the moon and placed it on a crater that will outlast every country currently on Earth. Long after NASA exists, long after the United States exists, long after English is a spoken language, that crater will still be called Carol, a widower's tribute written onto a world. The Artemis II crew also took one of the most extraordinary photographs in the mission's entire archive on their way home. Looking back from deep space with the moon behind them and Earth ahead, they captured the Milky Way, the full spiral structure of our galaxy, dominated by two arms wrapping off the ends of a central bar of stars, visible in a single frame. From inside the solar system, you can't normally see the galaxy that way. Too much glare, too much atmosphere, too much light pollution. But out past the moon, with nothing between the camera and the void, our home galaxy became visible as what it actually is. A flat disk of 200 billion stars seen edge-on with Earth sitting roughly halfway out along one of its spiral arms. For a few minutes, 4 people looked out a window and saw where we live. Not the neighborhood, the whole address. That might be the deeper shift Artemis II represents. Apollo was about proving we could get there. The Cold War, the space race, the flag planted as a statement to the world. Once that was done, we stopped going. For more than 50 years, the moon was something we had been to. Past tense, a completed achievement, a checked box. Artemis is different. The stated goal is not to visit, it's to stay. A lunar base near the South Pole, sustained human presence, a staging ground for missions to Mars. Those 10,000 photographs are not trophies, they are reconnaissance. Which means the question the photos are really answering is not what did we see? It's where do we put the first human outpost beyond Earth, and how do we survive there? If you were standing on the rim of a permanently shadowed crater at the lunar South Pole, wearing a suit designed to survive temperatures that freeze nitrogen out of the air, you would look down into a darkness deeper than any night on Earth. The sun would sit at a low angle, barely grazing the horizon. Your shadow would stretch for kilometers. And somewhere in that darkness beneath your feet would be water ice that has not moved since before life existed on Earth. The temperatures in those shadows sit around 240 degrees C, colder than the surface of Pluto, colder than almost anywhere in the inner solar system. The ice there is preserved in a state so stable that it may contain chemical signatures from the early solar system, locked in place for 4 billion years. Comet fragments, meteoritic carbon compounds, volatiles that have been there since the planets were forming. If we can reach it, study it, and eventually extract it, we are not just solving a resource problem. We are reading a sealed archive of the solar system's first 100 million years. The South Pole of the Moon is a time capsule, and every image from Artemis II is helping us figure out how to open it without destroying what's inside. That is where the next humans are going. And the images from Artemis II are part of how we're finding the safest place to send them. This is why the photograph matters. Not because a single frame contains a scientific bombshell. Not because one picture solves the lunar dichotomy or explains the far side crust, but because the entire visual record of the far side captured by human eyes for the first time in 2 generations just expanded by thousands of high-resolution frames. Every one of them is a data point. Every one of them feeds the model. And the model that emerges from all of them is going to look very different from the one we've been teaching in textbooks for 50 years. The moon we thought we knew was a convenient fiction. A gray rock, scarred and silent, useful mostly as a symbol of what humans could do when we decided to try. That fiction is dying. What's replacing it is stranger, wetter, more geologically complex, and more scientifically valuable than anyone who watched the last Apollo liftoff in December 1972 could have predicted. It started in a very real sense with 4 people in a capsule called Integrity, looking through a window, taking 10,000 photographs of a place nobody had seen with their own eyes in half a century. The moon was never dead. We just stopped looking. And now, finally, we've started again. Thanks for watching, and I'll see you in the next one.